Welcome to qnawire.
In this problem, we're going to use the kinematic equations to determine relationships between factors on Earth and factors on Mars. And so at max height, Vy is equal to 0 because it went on its way up and now it's about to be on its way down. But at a moment, its velocity is 0. So for part A, I'm going to use the kinematic equation. Vy squared is equal to v naught y squared plus 2 acceleration in the y times y minus y naught. Now I just said at max height Vy is equal to 0, so I'm going to plug in that here. V naught y squared just remains that. And then 2ay, I missed a parentheses here. And then y minus y naught is the height, which I'm going to denote by capital H. Thus, ay times h is equal to negative v naught y squared over 2. And in the problem, we're told that they're ejected with the same velocity. And so that would mean that v naught y is the same on Earth as it is on Mars. And so this right-hand side is a constant. Whether we're on Earth or Mars, it's going to be the same value, so it's a constant. And if the right-hand side is a constant, that also means the left-hand side is a constant, since they're equivalent. And so that means that the acceleration of the Earth times the height of the Earth is equal to the acceleration on Mars times the height of Mars, which is just the left-hand sides for both the Earth and the Mars, since we know they must be the same. Now we can solve for the height on Mars. And it's equal to the acceleration on Earth over the acceleration on Mars times the height on Earth. And we're given the acceleration values. The acceleration on Earth is 9.8 meters per second squared, and the acceleration on Mars is 3.71 meters per second squared. So we can plug those two values in, and when we do, we get that the height on Mars is equal to 2.64 times the height on Earth. So because there's less acceleration on Mars, it's able to go more than 2 times as high than it is on Earth. Part B is going to be done really similarly. We know that a kinematic equation tells us that y minus y1, or y naught, is equal to v naught in the y direction times t plus 1/2 acceleration in the y direction times t squared. Now, we want the total time that it's in the air, so the final y minus y naught is going to be 0, because we're going to let it go all the way up and then all the way down, so that the total distance traveled, or the total displacement rather, is 0. When we plug in that the total displacement is 0 into this equation, we're able to cancel a factor of t. And when we do that, we get acceleration of y times t is equal to -2 times the initial velocity in the y direction. Now, the right-hand side is a constant whether we're on Earth or Mars, because we're told the initial velocities are equivalent. And so since the right-hand side is a constant, that also means the left-hand side is a constant. So once again, we have the acceleration of the Earth times the time that it takes to reach the ground on the Earth. It is equal to the acceleration on Mars times the time it takes for it to reach the ground on Mars. We can again solve for Tm, and we get Tm is equal to the acceleration on Earth over the acceleration on Mars times the time on Earth. Plugging in the acceleration values, we get that Tm is equal to 2.64 times the time on Earth. And so because there's less of a gravitational force, it allows the ash to stay in the air for longer and to go higher. And that is the end of the problem.